Welcome to chapter 9. In this chapter, we are going to do just 4 sections. Okay, so you don't need to do the entire chapter. That's sections 9.1, 9.2. Then we'll skip to 9.4 and do 9.6. We will not do 9.5. So just 4 sections. It's going to be much easier. We're now entering the fluid and then thermal part of the course. Okay. So today we'll talk about solids, liquids, and gases, the different states of matter, including plasma. Okay. In particular, you'll learn about density, pressure, and buoyancy. So we have 4 states of matter: solid, liquid, and gas, which predominate on Earth. And then we have plasma, which predominates in the rest of the universe, where, for example, in stars where the temperature might be very high. So plasma typically associated with high temperature. And we're going to introduce the basic properties of each of these states. Some of this will be familiar from what we did in the overview in the very first chapter. Okay, so solids have a definite shape and a definite volume. Yeah? So you can measure their volume and they have a definite shape. If you try to distort them, you provide a small force in a certain direction. Then when you relieve the force, the object, if it comes back, that's its elasticity. Okay. So often a solid is made up of a regular lattice where you have these round atoms here, and they are held in position more or less by some kind of bond, here represented in this model using springs. So the bonds can be represented by springs, which are elastic. They can collapse and go back to shape. So when you provide that force, what you're doing is to distort or compress or elongate the spring. Yeah? There's no actual spring in there. It's just a model. The model is a ball and spring model. Okay. In practice, those are electrical forces, which are these springs. Okay. So all these atoms, they are not stationary in a solid. They are always vibrating about their mean position or their average position. So in all 3 directions, X, Y, and Z, they are vibrating. And how much they vibrate depends on the temperature. Okay? At absolute 0 temperature, all vibrations would die down and these would be completely at their equilibrium positions. But nobody has ever achieved that. We will not achieve it. Okay. So I talked about elasticity already, which is small distortions, and then you release the object, it returns to its original shape. That's elastic. If you provide a force such that the object deforms permanently, then that's called plasticity. Yeah? Then it cannot return to its original shape and size. So if we take a common solid, say salt, which is NaCl, okay, sodium chloride. Let me just write that. So this model here, we're going to represent NaCl, sodium ions and chlorine ions. They form bonds. Okay, so we have 2 types of atoms here, and the black lines represent the bonds. The larger one is the chlorine atom, because we have chlorine is negative, yeah, and sodium is positive here. And chlorine is the much bigger atom. So the green ones are chlorine and the small ones are sodium. How do I know that chlorine is the bigger atom? You need to go through the periodic table, and hydrogen, helium, these are the smaller atoms, the lower atomic mass. Yeah? Okay. You can also have solids where you don't have that crystalline structure, which means you don't have the atoms sitting rigidly in those lattice-like shapes in periodic positions. You can have something that looks like this, where your atoms are now fairly randomly placed, and they are still bonded to each other, yeah? But we don't have that regular lattice pattern. So this is called an amorphous solid. An example would be graphite. Yeah? So 2 types of solids. In a liquid, remember how in a solid those atoms were held in position and they would vibrate about the mean position. In a liquid, they are not held in position at all. So they can randomly move inside the liquid. So this particle here, depending on the temperature, will be doing some random motion, okay? And so these particles are free to wander inside the liquid. They're not held by bonds. So a liquid has no definite shape, yeah? But it does have a definite volume. If I take a certain amount of liquid, if I pour it into a different shaped container, its shape will change, but its volume will remain the same. What about a gas? A gas expands to fill the space, yeah, and it's also easy to compress gases. So it has no definite volume, yeah. It takes the volume of the container. It also has no definite shape, takes the shape of the container. Its molecules are completely free to move and in fact have no linkage with each other, okay, no bonds. The average distance between the molecules is extremely large compared to the size of the molecule, so it's mostly empty space. We briefly mentioned that plasma exists at very high temperature, like in the sun. At that high temperature, the electrons are often freed from the nucleus, okay, for the atom. So we have charged ions, and those ions produce an electrically charged gas. So there are long-range electrical and magnetic forces in the plasma because of these charged particles, okay? So the first concept we need to understand, very simple concept of density. I'm sure you've done this many times before in grade school. Density is essentially mass per unit volume. So this is the definition. We write density with rho as the symbol, this Greek symbol rho. So I'll write how to pronounce it, RHO. Rho. And its units are going to be in kilograms per meter cubed. So this is the SI unit, yeah? However, if you look up density for many substances, you'll find it's often quoted in gram per centimeter cube. So you need to know the conversion factor, and it's quite easy for you to work it out. If you convert grams to kilograms and centimeters to meters 3 times, because you have centimeter times centimeter times centimeter, you will find that 1 gram per centimeter cube equals 1,000 kilograms per meter cubed. Okay? So be careful of units in density. So typically so here are some typical densities, okay? For solid, liquids, and gases. These are gases, these are liquids, and these are solids. And all of these numbers are written in the same units of 10 to the power 3 kg per meter cubed, or gram per centimeter cubed, yeah? And we see that the solids, let's say brass is 8.44, gold is 19.32, is typically higher than for liquids like water. It's 1 gram per cc, or 1,000 kilogram per meter cubed at 4 degrees Celsius. It's a good number to know. We often compare different densities to that of water. So it's good to know. Blood is just slightly denser than water. Mercury is much more dense, almost like a solid, yeah? But typically, liquids have lower density than solids. And then gases, look at the units here, 10 to the minus 3. So much less dense than the liquids, yeah? Air, 1.29 times 10 to the minus 3 times 10 to the power plus 3, so it's just 1.29 kg per meter cubed. Yeah? Density of most liquids and solids varies slightly with temperature and pressure. For gases, it varies quite a lot with temperature and pressure. Okay? So the higher normal densities of solids and liquids compared to gases implies that the average spacing between molecules in a gas is about 10 times greater than the solid or the liquid. Yeah? So we said that earlier, that the gas is largely empty space. Let's do a simple problem on this. There's relatively little empty space between atoms in solids and liquids, so that the average density of an atom is about the same as matter on the macroscopic scale, approximately 10 to the power 3 kg per meter cube, like we saw for water. Yeah? 1 times 10 to the power 3. The nucleus of an atom has a radius of about 10 to the minus 5, that of the atom, and contains nearly all the mass of the entire atom. What is the approximate density of the nucleus? So let's start by making a little sketch. Let me say that here is my nucleus and I'll color it in. So all my mass is in this very dense nucleus, and let it have some radius Rn, okay? So it's very small, I can't show that from the center to there, but that's the radius of the nucleus. And let's say this is the edge, outer shell of my atom. So this is Ra, the radius of my atom, yeah? So we are given the density of the atom as of the order of 10 to the power 3 kg per meter cubed. And we are asked for the density of the nucleus. So this is what we're trying to find out. And we know that density is mass per unit volume. So the mass is no different for the nucleus than for the atom. Yeah? Both have the same mass since it's all inside the nucleus. The electrons are very, very light, very low mass particles. So we'll ignore their mass. So density equals mass per unit volume. Mass is the same. The only difference is in volume. Both are spheres. So my volume goes as 4 by 3 pi r cubed, right? So I'm going to write that my density is proportional to, let's just change that simple. So I'm going to write density is proportional to 1 over r cubed. Can I do this? Yeah? Since the volume goes as r cubed. So now all I need to do is to take the ratio for the atom and the nucleus. Let me start with the nucleus on top, since that's the one I want to calculate. So if I take the ratio of my nuclear density to the atomic density, what should this be equal to? This should be equal to Ra cubed divided by Rn cubed. Yeah? Just from what we wrote up here. Solving this for rho n, you can see that what you need is the ratio of Ra to Rn, and in this case we're told that Rn is 10 to the minus 5 times Ra times the density of the atom after cubing this. And now you can insert your values and solve. And when you do that, you should check your results against mine. Yeah? So you're going to get the nuclear density as of the order of 10 to the power 18 kgs per meter cubed. Much, much more dense than the atom itself, which was 10 to the power 3 kgs per meter cubed. Why is it so much more dense? Because all the mass is there, but the volume is very much less than that of the atom. Okay, another simple problem. A trash compactor can reduce the volume of its contents to 0.35, their original value. So let's say we have some later volume, which is 0.350, an initial volume. Yeah? Neglecting the mass of the air expelled, by what factor is the density of the rubbish increased? So we're going to use the same concept here. My later density equals mass per liter volume, and similar formula for the original density, right? Then I'm going to divide my, okay, let's write it. Original density, mass per volume 1. And let's divide one by the other. What do we get? We get rho 2 over rho 1. The two masses cancel since it says neglect the mass of the air expelled. So that means all the mass stays within here. And we're going to get V1 divided by V2. substitute this in for V2, and you should be able to solve for the density increase in the rubbish. Yeah? As usual, when you do this, you want to compare your results, and you should get that the density changes by 2.86 times. Yeah? So your new density, rho 2, equals 2.86 times rho 1. Another problem. So we have lots of simple problems based on this concept of density. A reservoir, which is here, a reservoir who has a surface area of 50 kilometers squared and an average depth of 40 meters. What mass of water is held behind the dam? So here, it's assumed that you know the density of water. If it's not given in the problem, you need to look it up. It might be near the question, or it might be at the start of the paper where some constants are given to you. So I gave you this value here. This was not part of the question, the density of water. So you know density, you know volume from here, and you need to find mass. I think you can do this. Yeah? Density is mass per unit volume. You're going to solve for the mass. You're going to use the value of rho that I just gave you. That's the area times the height. That's the volume, right? Area times height is volume. And you should get mass as 2 times 10 to the power 12 kgs. Okay, specific gravity. This is a number where we compare the density of any substance to that of water at 4 degrees Celsius. So if you remember, I told you it's nice to know that water is 1000 kg per meter cubed at 4 degrees Celsius. This is pure water, okay? Because when we divide any other density by this, we're going to lose the units because they'll get cut out, and we'll just get a number. That number is specific gravity. So it's a dimensionless quantity, okay? Let's look at another concept, the concept of pressure. Pressure is force per unit area, okay? So if you have an object like a solid object like this cube immersed in any fluid here, it doesn't matter just now what the fluid is, let's take it as water. Then there's a pressure due to the fluid on the solid from all sides, and that force that is applied is always perpendicular to the surface. So here it's in this direction, which is perpendicular to this surface. Here it's vertical because our surface is horizontal, so we have a 90-degree angle here, and so on. This force per unit area is called pressure. So pressure is force per unit area, and the units would be Newton per meter squared, which we give a new name for called Pascal, written as PA. Okay, uppercase P, lowercase a, after the scientist Pascal, who did a lot of work in this area. So imagine poking someone in the arm, okay, slightly painful, but not very, you can tolerate it, versus giving an injection. Why is the injection so much more painful? If I apply the same force, whether I poke you or I give the injection, why is the injection more painful? So remember, the pressure is mass per unit, force per unit area. Let the force be the same. What about the area? The area at the tip of my finger is much greater than that at the tip of the needle, since the needle is very, very fine. Hence the pressure is much greater, so you feel greater pain. Yeah? Okay, do another simple problem on this pressure concept. The pressure exerted by a phonograph needle on a record is surprisingly large. So there's a needle in there that we can't see, that it creates a pressure on this record, okay? If the equivalent of 1 gram is supported by a needle, the tip of which is 0.2 millimeters in radius, what is the pressure exerted on the record in newtons per meter squared? So my pressure, let's start with the definition. So maybe force per unit area. What's generating the force? The pull of gravity. So m into g is my force. What is the area? Let's take it as 2 dimensions, so it's going to be pi r squared. Yeah. where R is this. It's just given to you as a circle, so that's the area of the circle. And now you can just insert values and do your calculation. And when you do that, you should get the pressure as 7.8 times 10 to the power 4 newtons per meter squared. Another simple one, I'm going to talk you through this. As a woman walks, her entire weight is momentarily placed on one heel of her high-heeled shoes. Okay? Calculate the pressure exerted on the floor by the heel if it has an area of 1.5 centimeters squared. So this area here. And the woman's mass is 55 kgs. So exactly like we did before, right? mg is going to be the force. Here's the area already given to you. You need to just make sure you're in MKS or SI units. And then solve for pressure as force per unit area. Let's read this in parentheses. In the early days of commercial flight, women were not allowed to wear high-heel shoes because aircraft floors were too thin to withstand such large pressures. That's interesting. So aren't you glad that we have modern technologies that you can wear high-heel shoes? Okay.